What's up, folks? This is Bari, Brown University physics grad student and black hole researcher. I want to start today's video with a little story. In fall of 2025, last semester, when I was in my first semester as a Brown University grad student, one of my friends, Shiv, came up to me and asked me a simple question. How does light orbit a black hole? At the time, I couldn't give an answer, but little did I know that over the course of the next 6 months, this question would actually become ultimately my entire research agenda. And so now my research is to figure out how not only light orbits a black hole, but how another black hole orbits a black hole. This is what is called a binary black hole system, when two black holes are orbiting each other in a kind of cosmic death dance, and they emit gravitational waves that we can detect down here on the Earth. These gravitational waves were first detected in 2016 by LIGO, the Laser Interferometry Gravitational Wave Observatory, and that's why the LIGO team won the Nobel Prize in Physics for detecting gravitational waves released by two black holes orbiting each other. But today I want to go back to that question that my friend had asked me and try to answer it in detail. How does light, or how does any object, orbit a black hole? I'm going to first start the video by giving you the answer. The answer takes only about 5 minutes to give. But how you get to that answer takes about half an hour. So first I'm going to give you the answer. That's only 5 minutes of your time. And if you want to know how to get to the answer, the extra half an hour of derivation, that will give you a much deeper understanding of not only how a particle orbits a black hole, not only how light orbits a black hole, but how you can generalize this approach to a black hole orbiting another black hole. So with all of that out of the way, let's first start with a kind of beginner's level introduction to a black hole. What is a black hole? I'm going to draw a picture of a black hole here. So a black hole is almost like a fictional object. It's kind of crazy that this thing even exists in real life, and we have a picture of it. But this is what a black hole is. It's a circle, it's a sphere, it's a ball out in space that has two key features. First of all, the black hole has this skin, it has this outer shell. We call this the event horizon of the black hole. The event horizon. And any object, could be particles, it could be light itself, any object that trespasses the event horizon of the black hole is doomed to fall into the center of the black hole. This center of the black hole is where space and time is warped literally to infinity. This center is called the singularity of the black hole. Singularity. And any object that crosses this event horizon is doomed to fall into the singularity. So imagine you have, for example, a beam of light. It's coming in close, 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 closer and closer, and then ultimately it trespasses the event horizon. No matter how hard it tries, the beam of light cannot escape, and it will eventually fall in to the singularity like this. Now, the gravitational field around a black hole is what makes it so special. A black hole is like someone stuck a knife into the fabric of space and time. Normally, flat space and time looks like a sheet of paper. It looks like this. Flat space and time is just like a flat sheet of paper, except for the fact that it's not 3 dimensions, but rather 4 dimensions. Flat space and time has 4 dimensions because we have 1 dimension of time and 3 dimensions, x, y, z, of space. So this is our 1 dimension in time, and these are our 3 dimensions in space. Now hopefully my mic is turned on. Okay, good. Now, for the black hole, here's what the gravitational field looks like. Far away from the black hole, we still have the gravitational field of a flat space and time. But as we begin to approach the black hole, space begins to bend. It begins to bend more and more until ultimately, when you approach the singularity of the black hole, the gravitational field actually looks like a cut. Looks like someone sliced space and time with a knife or with a razor blade. This is what the gravitational field looks like around a black hole. So just to make it look more three-dimensional, let me add some curves and fields to this. And so this is what we mean when we say that black holes are the most gravitationally dense objects in the universe. You can have planets, you can have stars, you can have neutron stars, but the most heavy objects in the universe are black holes. And this is why they're the most dense objects in the universe, because there's nothing that can be denser than something that literally cuts space and time in half. This cut, the reason why we say that space-time has a curvature of infinity at the singularity is because the Riemann curvature tensor literally has a value of infinity. It diverges at the singularity. Now, let's go back to that question of, this is a general exposition of what a black hole is, what it does, but how does an object orbit a black hole? Let's investigate that question now. To answer that question, it's going to take me about 5 minutes, but to really understand how we get to that answer, it's going to take more than half an hour, especially if, even if you haven't taken general relativity, you can, I hope that my explanation can be of some insight to you. So here's the idea. Let's first draw our black hole. So I'm going to draw 4 black holes. Here's our first black hole. Here's our second black hole. Here's our third black hole. And here is our fourth black hole. Okay? Why did I draw 4 black holes? Well, because there's 4 different orbits that you can have around a black hole. And I will illustrate that shortly after I make all of these black holes look 3D. Now, each of these black holes has a radius. This is called the famous Schwarzschild radius of the black hole. So let me just draw that over here. Here is our prototypical black hole. It has some Schwarzschild radius given by R sub s. The black hole has some mass, capital M, okay? And the black hole has a singularity right at its center over here. That's it. That's all you have to know about the black hole. Now we're going to begin illustrating the 4 different types of orbits you can have around a black hole. The first orbit is the simplest one, which is a circular orbit. So if you have some particle that's orbiting the black hole, let's say this tiny particle has a mass of small m, then the simplest possible orbit is simply a circular orbit that goes round and round and round around the black hole. That's it. It's a circle. So this is a circular orbit. Circular orbit. The next kind of orbit that a particle can have around a black hole is an elliptical orbit. An elliptical orbit is just like a circular orbit, except it has some ovalness to it. Or as we like to say it, it has some eccentricity to it. So an elliptical orbit has a point of closest approach. This we call the periapsis of the orbit. This is when the particle gets closest to the black hole and is moving the fastest. And the farthest point is called the apoapsis, when the particle is furthest away from the black hole and moving the slowest. And so here, a particle on an elliptical orbit is a second possibility for how you can orbit a black hole. The third possibility for a black hole orbit is what's called a plunge orbit. Or actually, before we get to plunge orbits, let's talk about hyperbolic orbits. If you have, for example, a comet that just grazes the event horizon or grazes the black hole, then the comet is going to be approaching the black hole. It's going to get to some point of closest approach, just like an ellipse, but then there will be no point of furthest approach because the thing will go back out to infinity. So this is called a hyperbolic orbit. Hyperbolic orbit. You could also have the special case of a parabolic orbit, but that's a very limiting case that doesn't really occur often. And the last case, the last possible orbit you can have around a black hole is what's called a plunge orbit. So a plunge orbit is when an object is coming in near the black hole and then it gets gravitationally pulled in to the black hole and falls in to the singularity. And this is what we call a plunge orbit. Wow. So these are the 4 different orbits you can have around a black hole. Now, this is all great, these are all pictures, but is there a way to summarize this as a plot or as an equation? And the answer is yes. The equation that summarizes all of these four different orbits is actually the conservation of energy applied to a black hole. Here's the equation for the conservation of energy applied to a particle orbiting a black hole. So the kinetic energy of a particle is expressed as dr d tau squared. I will explain what all of these terms mean in a second. First, let me just write down the equation. This is equal to the total energy of the particle, not squared, this is just convention, as I'll explain shortly, minus the potential energy of the particle. That's it. This simple equation gives you these four different kinds of orbits. In fact, we can plot this equation, and I'll do that in a second. First of all, let me explain what you're looking at here. What is this equation saying? It's saying the following. First of all, let's go term by term. This right here, E tilde squared, what does that represent? This represents the energy of our particle. So our particle is some small object that's orbiting the black hole, and it has some energy, E tilde. What is tilde? E tilde represents the energy per unit mass of our particle. Okay, so E tilde is actually the total energy of our particle divided by its mass. So it's a kind of normalized energy. And V effective here, V effective tilde here, is simply the potential energy of our particle. What is the potential energy of a particle near a black hole? I'm going to write that down shortly. Lastly, this term over here, dr d tau, is telling us how quickly the radius of our particle's orbit is changing. So for example, this right here is r, right? And you can see that dr d tau is going to be changing for a hyperbolic orbit, right? As the particle moves from far away to closer near the black hole. But for a circular orbit, observe that the radius of the orbit does not change. So for a circular orbit, dr d tau is actually 0, right? But for an elliptical orbit or a hyperbolic orbit or a plunge orbit, dr d tau is going to be a non-zero value. So this is just telling you how does the radius of the orbit change over time. And so for a circular orbit, this is equal to 0. But for an elliptical, hyperbolic, or a plunge orbit, this is not equal to 0. The radius is changing. The radius of the particle's trajectory is indeed changing. You might ask, what is this tau here? This tau here is the proper time of the particle. The proper time of the particle is simply the time measured by the particle as if it had some wristwatch attached to it. So I don't have my wristwatch with me right now. There is a clock on the wall, but I will not risk ripping it off the wall. And so that's the basic idea behind the conservation of energy applied to our particle. Now let's break this down further. Let's expand out that potential energy term. So then we can write this as the kinetic energy of our particle, dr d tau squared, that tells us how fast the radius changes for the particle's orbit, is equal to E tilde squared minus, let's see if I can do this in a way that maximizes the way we use space here. Let's erase this. Okay, let me write it over here. So dr d tau squared is equal to E tilde squared minus, here is the potential energy term, 1 minus 2m over r times 1 plus L tilde squared over r squared. Okay, now if it's your first time looking at this, you might say, whoa, what did you just write? Okay, so I'm going to explain what I just wrote. This over here is that potential energy term that I had simply written as V effective earlier. Now, we can make sense of this potential energy term in a couple of ways. First of all, we could derive this, which I'll do in the next video. Or we can look at limiting cases. Okay, limiting cases. So first of all, the first thing I'm going to do to make sense of this is draw out this potential. Okay, so once again, this is my potential energy. This is my potential energy, which I will refer to as V effective, the effective potential energy of my particle. And if I draw this out, here's how it's going to look like. So I'm going to draw a plot now. This is going to be the master plot for black hole orbits. On the x-axis of my plot, I'll have R. R is simply the distance. Oops. R is apparently off the screen. Never mind. So R is just the distance between our particle and the black hole. So for example, if I have my black hole here, and I have some kind of a hyperbolic orbit, then the R at some given time would be this, the distance between my particle's position and the singularity. So R is the radial separation between the particle and the black hole. And on the y-axis, I'm going to plot the effective potential, V effective here. All right. Now, here's what it looks like when I plot this graph. If I plot this thing out, I will get the following figure. Okay, so what are we looking at here? Okay, this is a very important plot to help us understand black hole orbits. The first thing you'll notice about this plot is it looks wacky, it looks weird. All right, let's look at this plot. Let's break it down step by step. First of all, where does a circular orbit fall inside this plot? Well, a circular orbit is when we have an equilibrium point in our potential energy, when the potential energy has a derivative of 0. So this right here is a stable circular orbit. This is a stable circular orbit for our particle. Whereas this maximum here is an unstable circular orbit, for our particle. So in fact, every particle around a black hole has two kinds of circular orbits, a stable one and an unstable one, if it has enough angular momentum, which we'll talk about in the future. So that's where the circular orbits fall in our plot. Okay, so this is a circular orbit. This is a circular orbit. Now, where do elliptical orbits fall inside our plot? Well, elliptical orbits are another kind of bound orbit. Bound orbit simply means that the particle is, well, bound to the black hole. And so elliptical orbits fall in this region where the radius oscillates between a periapsis R sub P and an apoapsis R sub A. And in fact, there is a simple equation relating these periapsis and apoapsis to the semilattice rectum and the eccentricity of the orbit. So I'll write that down here. R sub P is the semilattice rectum times the mass of the black hole divided by 1 plus the eccentricity. And likewise, the apoapsis is the periapsis times the total mass of the black hole divided by 1 minus the eccentricity. Okay, so that is all good. So we have covered our bases so far. So this is the elliptical orbit. This is an elliptical orbit over here. Now, okay, let's draw the black hole over here. Now we've covered 2 of our 4 orbits. What about a hyperbolic orbit? Well, a hyperbolic orbit looks like this. So a hyperbolic orbit looks like this. So a particle is coming in, closer and closer to the black hole. And then it gets to some closest distance, some point of closest approach. Let's call that R star. So this, for example, here is the R star in this case, R star. That's the closest our particle gets to this black hole. And then once it gets to that closest point, it goes out again and heads away infinitely far away from the black hole again. So this is a hyperbolic orbit. Hyperbolic orbit. And it looks as follows, where this is our black hole, right? So it seems like some of the figures are coming out of the screen. Hopefully that's better. And finally, we've covered 3 of our 4 orbits. What does a plunge orbit look like? A plunge orbit looks pretty special. This point, this x-intercept is 2m. That's our event horizon of the black hole. You can observe that by plugging in 2m over here. For the radius, the effective potential goes to 0, which is what happens at this x-intercept right here. So for a plunge orbit, what a plunge orbit looks like on this diagram is as follows. The plunge orbit happens when you have enough energy so that the particle simply, boom, just falls right into the black hole. Once it crosses this event horizon, there is no coming